Hello students, if you remember we were discussing in the last presentation about the bioclimatic skyscrapers, ecological skyscrapers, we talked about the Swiss Re, we talked about the Commerce Bank and how they brought in dramatic innovation in skyscraper design structurally in terms of their bioclimatic design, in terms of passive indoor thermal comfort, in terms of energy efficiency. They brought a radical shift, and this shift began primarily because the world became very conscious about the energy crisis, particularly after the oil crisis in 1973. You might have read about it, you can read it up. There was a massive oil crisis in 1973 and the world woke up to the reality that someday we may not have access to non-renewable resources like oil. We need to look at alternatives. Not only that, by the turn of the 20th century, we became more and more conscious of the fact that we are destroying our environment because of rising carbon emissions and global warming. Today, global warming and carbon emissions are a reality that faces us starkly in our face, and there is no architect of any major concern, of any major relationship with the profession who will not try to bring in sustainability and efficiency into his building design. Now, energy efficiency just doesn't mean efficiency with regard to energy, it also means efficiency with regard to materials, because there is another component of energy called embodied energy, energy that goes into manufacturing materials that comes into play. And if we have time in these series of presentations, in some place I will talk about these components also. But the real result is that by the end of the 20th century, in the beginning of the 21st century, we had started designing buildings with a lot of focus on environmental sustainability. There was a lot of consciousness about it. If you remember, I had begun the last presentation by saying that earlier they were designing skyscrapers with regard to operational efficiency, but environmental impact was not being considered. Now both factors had to be carefully considered. The other thing that happened is that as we move into the 20th century and the moment frame skyscraper, the standard glass and steel skyscraper came up, particularly with the works of Skidmore, Owings and Merrill and of course Mies van der Rohe. The tremendously beautiful skyscraper like Seagram that came up left. Now the realization came that other innovative technologies are possible, primarily because we wanted to build taller skyscrapers. I will again repeat the thing that I had probably told to you earlier, that up to 150 meter is a tall skyscraper. 150 to 300 is a super tall skyscraper, and above 600 meters it's a mega tall skyscraper. We have just about 3 megatall skyscrapers today, the LBR&A Tower in Mecca, then there is the Merdeka in Malaysia, and there is of course the Burj Khalifa. But because of these skyscrapers, the need to go taller and taller required far more innovative structural systems than the moment frame, and that became possible because of the contribution of Fazlur Khan, who came up with many innovative structural systems which we will see later. Let's now start this presentation with a super tall building, and that is the Taipei 101, which at one time was the tallest building in the world. Its height is 509 meters and it was inspired by traditional Chinese architecture shaped resembling a pagoda, also can be like that of a bamboo shoot. The section tower is inspired by the bamboo plant, a model of strength, resilience and elegance. This is what I was talking about, the various levels of what the skyscraper is: tall, super tall or mega tall. Now it's got a 5-storied retail mall, and behind that is the 101 storied office tower. The structural design is based on the mega column and mega frame layout. This is, for example, the mega column. This mega column is 3 meters by 2.4 meters. It has got studs in it, it's got internal ties in it, it's got welded splices in it, and then it is filled up with concrete. So these are steel boxes, these mega columns filled with high strength concrete, and they form the basis of this mega structure of Taipei 101. There are 8 sections of 8 stories each within the Taipei 101. These sections and the top spire are shaped resembling a bamboo stalk or an elongated pagoda. So the 8 sections can be like the sections we see in a pagoda. At the base, the large steel columns, they slant or incline outwards as they go down to resist the lateral forces. Now the tuned mass damper, which is one of the key features of Taipei 101 and which prevents the building from swaying too much in either direction. It's 800 tons, 6 meter of dia ball of welded steel plate suspended from cables like a pendulum and working on the principle of inertia. It hangs inside the top of the building and it is visible even from the restaurant and bar of the building. And how it functions, very simple. When the building sways in one direction, because of inertia, it doesn't sway, and thus it is able to pull back the building from the sway to its original position. It helps stabilize the towers in high winds and in earthquakes, and also reduces the sway as a result of typhoons. This is how it is hanging in the building somewhere at the top of the building. Occupant comfort increases during strong winds due to the tuned mass damper because it damps the sway. It can reduce the tower's movements by up to 40%, and the TMD components were made in Canada, France and Italy, and except for the massive steel plates that were made in Taiwan itself. The visitors in the restaurant, in the bars, the observation decks between the 88th and the 92nd floor are able to see this huge gold ball of 600 tons. And it has been said by, I think, one of the people of the building that this serves as a source of comfort to the people that they are safe because of this massive damper. So when high winds and earthquakes result in swinging of the pendulum, it is restrained at the bottom of the sphere here. Large steel pins of 60 centimeter diameter engages piston dampers. There are these piston dampers in the surrounding restraint ring. There is a restraint ring here at the bottom. These are the piston dampers and they restrain the ball from moving too much, and the TMD offsets the wind induced motion of the building. Otherwise would have been a tremendous sway the people would have experienced. So because of this, as you can see here, as the building sways outwards, the mass damper remains where it is and is able to pull back the building to its original position. So Taipei 101 has the most innovative feature of the Taipei 101 besides the mega structure is the tuned mass damper. Now when we come to the Hearst Tower, again another project by Norman Foster in 2006, not a very tall building, just a tall building mounted over an existing Art Deco style base structure designed by Joseph Urban in the early part of the 20th century in Yellowstone with sculptures. This is that building. Norman Foster erected the iconic headquarters of the Hearst company and over the 6-story base, and he used a digrid frame to make this building. Now this building was the first commercial office building to get the LEED Gold certified rating for core and shell interiors in New York, and the way the US Green Building Council considered it for this certification was, number one, the innovations adhering to principles of sustainable design and construction. We will see that the types of construction products, finishes and furnishings used by Foster in the design, the use of water and energy, the selection of the site itself, waste management and indoor environmental quality. My students, I would again remind you that though I am taking you through these examples in a very summarized manner, you can pick up the information from my slides and then go online to go into greater detail about individual aspects that I am discussing in my presentation. Now this building saves both space and materials. Let us look at the material part first. Because of the perimeter digrid system, it saves 20% structural steel as versus a moment frame structure. That means if such a tall building was designed by Mies van der Rohe or Skidmore, Owings and Merrill in the moment frame structure, they would have consumed 20% more steel, or rather this building has consumed 20% less steel than that frame, and that is primarily because of the digrid frame. Not only that, the structural steel used in the building, 90% of it is recycled steel. As a result of this, 85% of the original structure can be recycled for reuse. Such an important basis for this certification. There is so much of reuse and recycling possible in this building. Now when it comes to the diagrid frame itself, no horizontal steel beams are used, as I mentioned when I was talking to you about the Swiss Re building. Each triangle in the diagrid is 4 stories or 18 meters tall, and because of this 20% less steel is consumed. Up to about 2000 tons of steel has been saved in this building. Now the diagrid frame itself results in these steel tube mega columns filled with concrete. These are those steel tube mega columns filled with concrete and placed along the perimeter up to the 10th floor. And then there is this skylight that is 12 meters from the perimeter of the original facade to the perimeter of the new tower. This is 12 meters of skylight provided in the building. So when you are at this level, tremendous amount of light filters into the atrium. Each steel and concrete floor plate is also 12 meters column free span, and the structural elements of the main lobby start at the 3rd floor, rise to the 10th floor, and also serve as lateral elements for facade. So you can go into these details about this building, you can study a little bit more online to understand the structure more clearly. But when we look at this building, the entire facade of the low height base, the original base, has been preserved, but it has been dug out, it has been completely scooped out, and this 7-story atrium has been provided within. The vertical glazing along the perimeter of the original tower here is a clerestory from 7th to 10th floor, and it illuminates the atrium along with the other lighting provided here in the atrium. So the atrium ceiling and clerestory visually connect the old and the new structure. So both the buildings, this atrium space, this entire old building that has been converted into an atrium, provides the connection between the older and the newer part, and leads down further into a waterfall here, which is not visible here clearly in the picture. There is a water cascade, rather, a water cascade flowing down towards the underground part of the building. So when we come to another building, the New York Times building in New York by Renzo Piano in 2000 to 2007, this building has a very strong urban presence, and what it does is it makes energy efficiency its goal, along with being very light and transparent in its visual appearance. So it has got a permeable public space. If you look at the ground floor plan here, you find that you can enter this floor, public can enter this floor area from the streets, and this gives rise to social activities and interaction. In fact, what is it actually? It is a privately operated public space, as I talked to you about in the earlier presentation about POPs. It has got retail stores, it has got restaurants, it has got supermarkets, and it has got this central courtyard that you see here, and it's got an auditorium here looking towards the courtyard, as you see here. And so there's a lot of activity for people available in the ground level of the building. Auditorium is for small plays and lectures, etc., and towards the east side the services have been provided. The 6-story base of the tower, this is the 6-story base, which is having the atrium for the shops, the restaurant, the auditorium for lectures, that all is accommodated in the 6-story atrium. Now in the facade there is the glass curtain wall, but in front of it a very unique system has been arranged by Renzo Piano, and that is providing a sunscreen of ceramic tubes. And what it does is that these white ceramic tubes, about 186,000 of them, help to provide shade to the glass facade. They help to reduce the heat gain coming on the glass facade, and have led to a very unique aesthetic appearance of the skyscraper in New York. Now therefore, because of the following reasons, this is a LEED gold certified building. incorporating these energy efficient systems. One is the ceramic sunscreen that lowers the temperature coming indoors, the daylight coming indoors, and thus helps in indoor thermal comfort. There is therefore a high performance facade, state of the art lighting system has been used, and there is a rainwater harvesting or a rainwater collection system in the building. Now I have talked to you about these two buildings, the Hearst Tower, which is also LEED Gold certified, and I have talked to you about this building which is also LEED Gold certified in its area. What is LEED actually? You might have heard about it, Leadership in Energy and Environmental Design. It's a green building rating system. In India, there are two rating systems that we use. There is the LEED IGBC, the LEED India Green Building Council, and we use the GREHA system. So these two are being used by us. LEED by itself has been developed by the US Green Building Council, internationally recognized certification program for green buildings, which applies for a wide range of projects including residential, commercial projects and public spaces. The points are given based on sustainability measures that are implemented within the building design, in the construction and the operation of the building, and the points determine the certification level. So if you look at the points in the certification level, a building is just LEED certified at 40 to 49 points. If it scores 50 to 59, it gets a silver certification, 60 to 79 gold, and 80 plus points it gets a platinum LEED certification. And there is an entire manual available, and if you have it in front of you and you design your building according to the pointers given there, you can apply for the certification for your building. Now the types of LEED certifications that are available, there is the building design and construction, there is interior design and construction, operations and maintenance, neighborhood development, and there is one LEED specifically for homes. So yes, there is a lot of advantage in trying to design LEED certified buildings, and a lot of commercial ventures are also endeavoring to have LEED certified buildings when they advertise for them, because it provides a certain consciousness among people or gives them the awareness that this building is an environmentally conscious building. Now what all are the key LEED categories? There is the sustainable sites category, minimizing the environmental impact on the building site. So while the building is being constructed, what all can be done to reduce the impact while the construction is going on. Then there is water efficiency, reducing water use through efficient systems and practices while the construction is going on and later on when the building is operated by the people who occupy it. Energy and atmosphere, EA, energy efficiency using renewable energy and reducing carbon emissions or greenhouse gas emissions. Materials and resources, use sustainable materials in construction and minimize construction waste on site. Improve indoor environmental quality by enhancing indoor air quality, lighting, comfort, even the sound quality inside the building. Innovations, IN, points to creative solutions and strategies used within the building, and regional priority refers to addressing regional specific environmental issues. So these are the key LEED categories. So I have digressed from my discussion of the tall buildings and skyscrapers to give you a brief description about the LEED program, so that you, if you are keen or interested about the LEED program, leadership in energy and environmental design, you can pick it up. You can actually get a LEED AP, LEED accredited professional certification, and you can design buildings based on the LEED certification program. Now the building, this New York building, the New York Times building by Renzo Piano, is also a part of what is called as high-tech architecture. I have not yet touched upon it. I will be touching upon high-tech architecture when I talk to you about styles and movements. This was a specific branch under late modernism, and this deals with buildings that have use high technology and they resemble high technology in their features, in their appearance. And one of the key features is lightness and transparency. The building appears light and transparent, and so that is true for the New York Times building. Then this lightness and transparency is also visible from the interior of the New York Times building. Another thing that happens in the New York Times building is the extension of the glass facade above the roof level, above the building height, so to speak. And so we find the same thing happening, for example, in the Shard and in other buildings also, where the glass curtain wall has been extended above the actual building height. Now let us come to another interesting building, the first interstate world center in Los Angeles in California by Pi Cobb Fried and Partners in 87 to 89. So we are going back a little bit to look at this building. The reason why this building is important is because it is dealing with two diametrically opposite issues but provides one common solution. The two issues were, it was supposed to be the US, now it's called the US Bank Tower. It is 310 meters tall, so it's a super tall building, and in this part vertical architecture was not suited because of the high seismic risk and many faults that are there in this site. But they were also committed to preserving the historic architecture of this area, and also they desired a landmark city center. So in the first case you should not design tall. In the second case, you are required to design tall so as to preserve the historic architecture, not to demolish it by having a linear spread of a building, but also you need a landmark city center feature, which is a tall building. How do you reconcile these opposing things? How do you make a building which is tall but has seismic safety in it? So Taipei 101 all over again, that same concept of that we need to make it seismically safe. And this building in fact has been designed for a seismic resistance magnitude 8.3 on the Richter scale. Local earthquake conditions defined structural system and resulting composition. The framework that was required to meet the conflicting demands, we required the frame to have flexibility for this earthquake, and we required rigidity to confront the wind forces, and this kind of structural hybrid system had to be built. Now the geometric and structural elements are combined to create an iconic architectural identity. This visual that you see here is a simulation of how the building responds to one of the 32 vibrations to which it has been subjected. So here it is, the combination of two structural systems. There is the outer steel frame and the outer perimeter, which is ductile, it is flexible, and it absorbs the seismic movement or the earthquake movement. The inner core inside is rigid, it is a square internal rigid core which faces the lateral forces of the winds, the high velocity winds. Based on the internal core reinforced with, now two systems have been provided, the outer steel frame, ductile core, frame, and the inner core rigid. And in the inner core, because we wanted to have tall windows at the ground level so as to provide a street level experience for the building, the base of the internal core here, as you see, has been reinforced with 2-story high braces at the base. And as a result of this, the tower's large window openings have been made possible at the base, and as you can see in this picture, there is an apparent lack of structural elements. So how innovatively structures have been evolving in skyscrapers to solve very typical problems. Now when we come to innovative skyscrapers, this is the second part of this presentation. I talk to you about some of the latest innovative skyscrapers coming up globally. Like two you see here, the Tianjin CTA Finance Center in China by Skidmore, Owings and Merrill in 2019, which is a super tall 530 meter skyscraper, and then the Central Park Tower in New York by Adrian Smith and Gordon Gill 2020, which is again a super tall 427 meter skyscraper. Now when it comes to innovative skyscrapers, what are we finding today? Number one, they are spreading throughout the world, including South Asia, including India. The shift is towards super tall and mega tall structures. They use innovative materials and construction technologies. They use building automation at a very high degree. They are all involved with energy efficiency. They all try to incorporate green building strategies and sustainable features. They are basing their design on the Internet of Things and AI, particularly in the last 5-10 years, and these systems and controls are used in these buildings, and they are also keeping an eye on seismic safety. So let's come to Merdeka on 18 in Kuala Lumpur, Malaysia, which is now today the second tallest building in the world at 678.9 meters, 118 floors. It's a mega tall building. Its triangular shaped glass facade limits heat gain, maximizes natural light in the way that it has been designed, and reduces energy consumption. This is designed using the principles of what is called as parametric design, and as a result of these amazing digital tools and technologies, we are today able to conceive forms of skyscrapers and other buildings which could have never been able to conceive even 20 years from today. But because of these computer aided design tools that we have, CAD tools that we have, we can consider, or we can imagine such amazing forms, and we can practically imagine that they can be built. But there is another side to it. If there is CAD, then there is an addition to it today, and that is called CAM, computer aided manufacturing. We are able now, using computer aided tools, to manufacture sub parts and sub assemblies of buildings. And not only that, even on site, amazing new construction technologies have now come in that help us to execute the imagination of the architect on the digital tool, on the digital system. So CAD plus CAM plus modern construction technologies are making these amazing forms and shapes possible today. So this triangular, this facade, along with being limiting heat gain, maximizing natural light, and reducing energy consumption, it is also having a hydrophobic coating. What does this mean? Hydrophobia? Hydrophobia is fear of water. This coating has, in a sense, fear of water. The water is washed away, the dirt is washed away by the rain, and this helps in reducing the maintenance cost of such a tall skyscraper. It's also got LEED Platinum certification for low energy systems, smart ventilation, and water recycling. It has got artificial intelligence driven intelligent climate control systems. We were talking about building automation control systems in Commerce Bank in 1997. By the time we have come in 2023, just about 26 years later, we are talking of AI driven intelligent climate control systems, in which the air conditioning is based on the occupancy levels, on the number of occupants in a room, and based on that the air conditioning load can be increased or decreased. And this is all controlled through sensors. Lot of interesting study and research is going on even in IIT, where we are trying to understand how we can devise systems which can be occupant centric. Along with that, there are automated blinds which regulate the sunlight exposure. Another interesting thing, and this is very important for a mega tall structure, is that it's got an automated self-climbing formwork which climbs the building side and keeps building it as it keeps rising in height. Along with that, the Internet of Things protocol sensors are used for adjusting lighting, air conditioning, and elevators based on real-time occupancy information. Specially designed evacuation sky bridges. As you know, that sky bridges are vital for super tall, mega tall buildings, particularly because evacuation in these buildings in case of a fire or emergency can be very difficult and requires a lot of different techniques to be tried. One of the ways in which we do that is by providing sky bridges or evacuation sky bridges to offer safe escape routes from the high levels. Another building, or rather a set of buildings, rather two towers, the Manhattan West that has come up in New York, again designed by Skidmore, Owings and Merrill in 2023. They are not very tall. One is 285 meters, 58 floors high, the other is 303 meters, just touching super tall at 67 floors. But the interesting part is where they have been put together. They have actually been constructed by building a 2.6 acre platform under which are running live rail tracks. Because of the rail tracks, this platform had to be built over the rail tracks in order to support these massive towers. And this led to the buildings being organized around series of plazas automatically, or that organically resulted as a result of the platform. The AI based HVAC and lighting systems are used in the building, and AI based elevator dispatch systems are used to reduce waiting time for people and also to reduce energy consumption. Another building, now this time in Mexico City in South America, in Mexico, the Torre Reforma by LBR&A, which is not very tall, it's 246 meters at 57 floors, but it is the tallest building in Mexico City, sustainably designed. It is known for its triangular concrete structure. The triangular shape is to provide stability in the case of an earthquake. So, it has got an earthquake resistant cantilevered core, thus making it an earthquake resilient skyscraper. It's got a self-sustaining energy system of solar panels and rainwater harvesting. It's got green walls and natural ventilation to enhance indoor air quality and reduce the overall carbon footprint of the building. So, we see buildings in China, we see buildings in Malaysia, we see buildings in United States, now we are seeing a building in South America, in Mexico. We see buildings in Russia, we see the Lakhta Center in Russia, which is now the tallest skyscraper in Russia and Europe at 462 meters, super tall building at 87 floors. It is the world's tallest twisted tower using high performance glass. Its twisted shape, 90-degree rotation, enhances wind resistance and the structural integrity of this tower. It's got a triple layered glass facade which minimizes heat loss and reduces energy consumption of the building. It's got also automated lighting, heating and cooling systems and reduces the overall energy consumption of this building by 40%, thus making it energy efficient. Repeatedly, as I am taking you through these innovative buildings, innovative skyscrapers, we are mentioning the same things over and over again. Efficient use of resources, efficient use of energy, use of automated systems, AI technology, IoT for energy, for seismic safety, for rainwater harvesting, for sustainable features, all of it, gamut of issues are being covered by these skyscrapers. Or we have the Ping An Finance Center in Shenzhen in China, which is standing at 599 meters, just a meter short than megatall at 115 floors, and it is an AI powered smart skyscraper with a smart HVAC system that automatically adjusts the temperature and airflow, again based on occupancy. This is another again pointed out to you because this work is being done in the IITs. We are working on occupant centric design, where earlier 20 years back the design was we do simulation modeling and thus we are able to design buildings and make them energy efficient by lowering the air conditioning load. But now we are focusing on how we can make it not just efficient for a room, but efficient for individuals. How we can increase or decrease the load, how it can sense the amount of occupancy in a room, whether it's gone up, gone down, or even what the occupant's level of comfort is with regard to air conditioning. So, lot of fine grained studies are going on today, and some of these studies, after having undergone the kind of research work involved in it, are now becoming realities in many buildings today. IoT enabled workplace optimization uses real-time occupancy sensors to manage the utilization of office space and thus reduce unnecessary energy waste, and therefore it is able to reconfigure office spaces based on the occupants or how the occupants use the space within. The AI enhanced smoke detection system is for fire warnings, early fire warnings. So, we have covered these skyscrapers that talk to us about these innovative features. The buildings that I have covered are by no means exhaustive. There are far too many buildings that are being built today having these innovative systems and features in them, and it is up to you now, taking interest from whatever little I have talked to you, to go online or to go to your books and read more about other such innovations and innovative skyscrapers, and read in detail about some of the points that I have mentioned here about these particular buildings. I will end this presentation by giving you a series of skyscrapers that we began with a couple of presentations back. Iconic skyscrapers, whether they were the Chrysler Building, the Empire State Building, or it was the Space Needle in Washington by John Graham and Co. And then later on, and I will touch upon the two of these skyscrapers, the John Hancock Center and the Willis Tower, when I talked to you about structures in skyscrapers. And then there is also the Trans-America Pyramid in San Francisco by William Pereira. There is this, later on as we keep moving, we see the forms fundamentally transforming in skyscrapers, and we get the CN Tower in Toronto, Ontario in 1976, which is 553 meters tall, the Oriental Pearl Tower in Shanghai, China 1994, 468 meters tall, and the Petronas Tower is 451 meters 4.9 meters tall in 1998. We have the Burj Al Arab Hotel 321 meters tall. We have the Jin Mao Tower in Shanghai at 348. We have the Taipei 101 at 508.2 meters. We have the Turning Torso in Sweden, the Akbar Tower in Barcelona, the Shanghai World Finance Center in China. We have the Burj Khalifa, the tallest building that is there today, with the One World Trade Center that came up with the destroyed World Trade Centers. And then we have the Canton Tower in China, which is 449 meters high. We have the Marina Bay Sands at 206 in Singapore, Al Hamra Tower in Kuwait City, and the Abraj Al Bayt Tower in Mecca, which is also at 494. It is actually in fact higher than this. I hope that we'll get our figures correct, because it falls within the category of close to super tall, nearly touching mega tall. And then we have the Tokyo Sky Tree, we have the Shard, and we have the mega tall Shanghai Tower in Shanghai, China. We have the Evolution Tower in Russia, the Abode 318 in Melbourne, Australia. We have the pin-thin skyscrapers, the pencil-thin skyscrapers, 432 Park Avenue, New York by Raphael Vignoli. Unfortunately, not been able to cover it. Maybe we might cover it when we come to residential design projects. We have Merdeka 118, I have seen this with you. We have the Manhattan West, I have seen this with you. We have the Torre Reforma, I have seen this with you. So, coming to the very end of this presentation, let us look at the super tall and mega tall skyscrapers of today. The One World Trade Center stands at 541.3. It is a super tall one. Lotte Tower in Seoul is 555.7 meters. I discussed about this tower with regard to its public spaces a couple of presentations earlier. We have the Ping An Finance Center in Shenzhen, just touching the mega tall point at 599.1, and we have the definite super mega tall in the Shanghai Tower at 632, the Merdeka at 678, and like I said, Abraj Al Bayt Mecca, if we take the total height, is at 601 meters, and the tallest of all, the mega tallest of all, is the Burj Khalifa. So in fact, there are 4 buildings today that are lying in the mega tall category, and many buildings lying in the super tall category. We'll end here and we'll continue from here with structures in skyscrapers. Now it's very interesting to see the kind of structures that came up and the kind of forms they resulted in skyscrapers. We'll see that in the following presentation. Thank you.